Every system seeks balance, but space shows us that stability is just a brief pause between eras of chaos. Stars are born, explode, and reshape the space around them. They leave scars that define entire regions of the galaxy for millions of years. The region of the Milky Way closest to us offers a striking record of ancient cosmic upheavals. The space where our solar system drifts was shaped by a series of supernova explosions, carving out the local bubble, an enormous void more than 300 light-years across. Right now, we're speeding through the sparse, hot hydrogen of the local interstellar cloud, itself wrapped in a shell of cold gas. And this is just a tiny patch on the edge of the Orion arm of the galaxy. Nearby, only about 400 light-years away, a searingly hot neutron star cools down. It's the ultra-dense remnant of a massive star, known as the star RxJ 1856.5-3754, the leftover from a cataclysm that happened a million years ago. So what does this complex, invisible structure of near space actually look like? What shape does the space immediately surrounding Earth take? Today, we'll break this down step by step. We'll take each object, every structure, every scar left by an ancient explosion, and piece together the true face of our cosmic neighborhood. From the nearest stars to colossal bubbles of scorching gas, from seemingly peaceful clusters to runaway stars flung by explosive shockwaves at terrifying speeds. And by the end, the picture that emerges will look little like the empty black void you see in textbooks. But first, let's talk scale. The Milky Way galaxy holds around 200 billion stars. 200 billion. That's one star every second for over 6,000 years, just to count them all. And each of these stars has, on average, at least 5 planets orbiting it. That means our galaxy contains no fewer than 1 trillion exoplanets, worlds we know almost nothing about. Here's the fascinating part. We don't have to look far to get lost in these numbers. Within just 50 light-years from the Sun, a stone's throw on a galactic scale, there are about 2,000 stars. 2,000, not 10, not 100, 2,000 distinct suns, many with their own planetary systems, their own stories, their own catastrophes. And they all fit inside a sphere that looks like a pinprick on the map of the Milky Way. Now here's the detail that's hard to wrap your mind around. Step outside on a clear night. Look up. The sky above you is black. You might see a few thousand points of light if the weather and city glow cooperate. It feels like an absolute ringing void. But those 2,000 stars, they are all there, right now, surrounding us. Most are too faint to spot with the naked eye, but they exist. They burn, spin, and pull in dust and planets. The space between them isn't empty. It's filled with the hot gas of the local bubble, the very structure carved out by supernova explosions millions of years ago. This isn't a void, it's an environment, a tangible, physical space with temperature, density, and definite borders. Let's circle back to that neutron star with the designation RxJ 1856. It was discovered in the 1990s, but not with ordinary optical telescopes. It's nearly invisible in that range. Instead, X-ray observatories detected its signature high-frequency radiation. This object is all that remains of a star that once was several times more massive than our Sun. About 1 million years ago, it exploded. The shock wave from that explosion is one of the very waves that shaped, and still shape, the walls of the local bubble. In other words, we live inside the aftermath of its death. 400 light-years separate us from the nearest stellar corpse. The cavity scorched by a series of such explosions stretches over 300 light-years across. Around 2,000 stars circle nearby, and the temperature of the interstellar gas surrounding our solar system right now, it's hundreds of thousands of degrees. But if this is not empty space, but a structure with walls, boundaries, and a hot interior, then a question arises. One I don't yet have a simple answer for. Where exactly is our planet rushing through this blazing gas? And what awaits it on the other side of the bubble? The answer is already here. Right now, this very second, Earth sits inside what's called the local interstellar cloud, a small pocket of warm gas and dust nestled within the larger local bubble, like a pit inside a peach. This cloud stretches about 30 light years across. The solar system entered it relatively recently, on a cosmic scale, and it's moving through it at roughly 26 kilometers per second. This isn't stillness, it's a journey. And this journey has a destination, even though no one picked it. In about 8 million years, the solar system will leave the local interstellar cloud and enter a region astronomers call the Loop 1 bubble. 8 million years sounds like forever. But to put that in perspective, dinosaurs vanished 66 million years ago. So our trip to the next zone takes about 1/8 of that time. Not that far off. And this is where the map of our investigation expands. The Loop 1 bubble is a super bubble, massive, roughly the size of our own local bubble, and partially overlapping with it. Imagine two giant cavities filled with hot, thin gas, their walls touching and even merging in places, like two soap bubbles stuck side by side. The center of Loop 1 lies about 500 light years from Earth, near the bright reddish star Antares, the alpha star of the Scorpius constellation. This is the very star you can spot on summer nights with the naked eye, low along the horizon. It glows red, standing as a landmark pointing roughly in the direction we're headed. But who carved out this cavity? Where did a bubble hundreds of light years across come from? Inside the loop. One bubble lies a massive stellar association known as Scorpius Centaurus. Recent estimates count more than 2,000 stars within it. But this isn't a dense, tightly packed cluster held together by gravity. Instead, it's a loose grouping, stars scattered across tens of light years. They share a common origin, but not a shared orbit. Many of these stars are massive, hot, and blue, the kind that burn bright and die loud. One leading theory suggests that around 15 million years ago, several large stars in this association exploded in a kind of chain reaction. Not just one. Multiple stars went supernova, possibly stretched out over a couple million years. Each explosion sent out powerful shock waves. Those waves overlapped and combined. Gas got pushed outward. The result? A vast cavity, scorching hot, nearly empty, surrounded by dense walls made from the ejected material. That cavity is the Loop 1 bubble. Or more precisely, its skeleton, the scar left behind by a series of violent stellar deaths. Simply put, the Scorpius-Centaurus association is a supernova factory, and it's still firing on all cylinders. Stars here continue to form, age, and explode. That means the bubble our solar system is moving into isn't some frozen relic. It's alive and active. Now, let's look inside. The temperature of the interstellar gas in this region of the galaxy soars above 1 million kelvins. 1 million degrees. That's 170 times hotter than the surface of the sun. It sounds like instant death for anything caught inside. But here's the paradox. At that temperature, the gas is almost imperceptible. Its density hovers around 50,000 atoms per cubic meter. By comparison, the air we breathe holds roughly 25 quintillion molecules in the same space. It's like cranking an oven to its maximum heat, but placing exactly one molecule of dough inside. Technically, it's scorching. Practically, there's nothing to transfer the heat. This is one of those cases where the word temperature means something very different than what we're used to in the kitchen. In plasma physics, temperature measures the average speed of particles. These particles race at incredible speeds. But there are so few of them that collisions barely happen. The gas is scorching hot, but nearly empty. Heat without fire. Yet this blazing gas isn't entirely harmless. The high temperature of its particles creates a faint but high-frequency radiation, a soft X-ray glow filling the entire bubble. It's this glow that first allowed astronomers to spot these structures. X-ray telescopes detected a smooth, gentle background, and for a long time, no one could explain where it came from. But for hypothetical life on a planet like Earth, this background isn't a death sentence. The stellar wind, a stream of charged particles from the home star, deflects most of the high-energy radiation long before it reaches the planet. What does get through gets absorbed by the atmosphere. Multiple layers of protection, each working on its own. It creates a strange picture. The solar system speeds through a medium heated to 1,000,000 degrees and feels nothing. The gas is too thin to burn us. The radiation is too weak to penetrate the atmosphere. We literally cross the boundaries of structures scorched by chain reactions of dead stars and come out unscathed, for now. If bubbles are scars and star groups like Scorpius Centaurus are the sources of those scars, then a new question emerges. Stars within these groups don't last forever. They drift apart, scatter, and lose connection with one another. Some clusters that now appear as fixed points in the sky are already breaking down, slowly, quietly, but inevitably. The Hyades stand out as one of the most recognizable star clusters in the winter sky. Humans have watched them for thousands of years. The ancient Greeks named them, Arab astronomers charted them on star maps, and through all those centuries, no one ever questioned whether this cluster would still be there tomorrow. Of course it would be. It has always been there. The stars hold together like stones in a wall, tight, steady, eternal. But that's not true. The Hyades lie about 150 light-years from Earth. This open cluster is around 650 million years old. At first glance, it looks compact. A dense core about 10 light-years across, surrounded by a tidal zone stretching roughly 30 light-years. 30 light-years. That's about the size of a small urban neighborhood. Close-knit, lived in, familiar. It seems everything is in place. The stars inside, held by gravity. The system, stable. The year is 2018. Astronomers examine the motion of hundreds of stars around the Hyades, not just their positions, but the direction and speed of each one. And then they discover something no one had ever seen before. Two long stellar tails extend from the cluster, not just tens of light years, not hundreds, more than 2,500 light years. Simply put, the cluster, the dense core we've known as the Hyades, is just a tiny center. The true Hyades are a stretched-out trail of stars, tens of times longer than what the naked eye can see. The Milky Way's gravitational pull slowly, relentlessly pulls stars away from the cluster, like threads unraveling from fabric. Every star caught in the tail will never return. Here's what's fascinating. Inside the Hyades cluster, you won't find a uniform sea of identical stars. Instead, there are more than 700 stars, with a total mass equal to 435 suns. Among them, 4 red giants loom large, bloated, aging, nearing the end of their lives. 9 white dwarfs linger. These are the dead cores of former stars, cooling embers in space. Then, 27 brown dwarfs drift, objects that never gathered enough mass to ignite nuclear fusion. This isn't a city in its prime. It's a city where some residents are dying, others never truly lived, and the rest slowly fade beyond the horizon, carried away by a current stronger than any local ties. And this city? It's falling apart. My friends, I have to say, there's something deeply familiar in this scene. We get used to the world around us staying steady, our homes, the streets, the people. So when they start to vanish, our first reaction is disbelief. Because just yesterday, everything was where it should be. But yesterday offers no promise for tomorrow, neither for a city nor for a cluster of stars. The Pleiades. 445 light-years from Earth, about 3,000 objects, with a combined mass exceeding 800 times that of our Sun. They are nearly 6 times younger than the Hyades, only 115 million years old. A young, bright, and dense stellar city. Nearly a quarter of its population consists of faint brown dwarfs, invisible without specialized instruments. The Pleiades look like a cluster at the height of its power, but simulations reveal their future without illusions. In 500 million years, only a few hundred of those 3,000 objects will remain, and by the time they reach 1 billion years old, just a few dozen will be left. The very same gravity of the galaxy that has already stretched the Hyades into tails thousands of light years long will eventually reach the Pleiades. It simply hasn't caught up yet. Here's a curious thing. A star cluster feels eternal because a human life is too brief to witness its slow unraveling. It's like a photo of a sandcastle. In the picture, it stands firm, but that photo was taken between two waves. The first wave has already gnawed at the base. The second hasn't arrived yet. And if you only look at the photo, the castle seems timeless. But look away, then come back 1 million years later, and the sky is empty. No cluster remains, no familiar pattern. The stars have scattered across the galaxy, each on its own, each alone. The night sky we're used to isn't a map, it's a snapshot of decay. Those patterns that seem carved in stone are actually painted on water, and the water is already moving. The gravity of a galaxy shows no mercy to entire star clusters. But sometimes, the most dramatic events unfold not from the outside, but deep within the star systems themselves. Here, two stars orbit so close they warp each other with tidal forces, hiding behind the deceptive glow of a single bright point. Spica, the brightest star in the constellation Virgo. A pale blue dot in a pattern the ancient Greeks linked to the goddess of harvest. 250 light-years from Earth, practically next door in cosmic terms. It's one of the brightest stars in the night sky, ranking 15th in visible brightness. You can find it easily. Draw a curve from the handle of the Big Dipper through Arcturus, and the next bright point along the path is Spica. One star, a single, steady, calm glow. Simple, except it's not. Spica isn't just one star, it's 5 stars. A multiple system made up of 5 components, all packed into a single point of light. And the real show is at the center, where a pair hides so close together that no telescope on Earth can separate them. 2 stars, Spica AA and Spica AB, orbit so close together that even the sharpest telescopes see them as a single point of light. They are visually indistinguishable. The only way to reveal that there are actually 2 stars is through spectroscopy. Their absorption lines split and merge in a repeating pattern, revealing the cosmic dance of a binary pair. In other words, the light itself tells a story the eye cannot see. And this is where the real mystery begins. What exactly hides behind this flickering duo? The larger of the two, Spica AA, is a blue-white giant. It weighs 11.4 times the mass of our Sun. Its radius stretches over 7.5 times larger than the Sun's. The surface temperature soars beyond 25,000 kelvins. For comparison, our Sun's surface sits at about 5,800 kelvins. Spica AA burns more than 4 times hotter. The result? It shines with 20,000 times the brightness of the Sun. Imagine 20,000 suns packed into a single star. Its companion star, Spica AB, is more modest, but only compared to its bigger sister. It holds 7.2 times the mass of our Sun. Its radius stretches to 3.7 times that of the Sun. The surface temperature reaches 20,900 kelvins. Its luminosity shines at 2,254 times that of the Sun. By any normal standard, this is a colossal star. Yet, standing next to Spica A, it feels like the younger sibling. But the distance between them, that's where everything changes. Let's try a thought experiment. The distance between Earth and the Sun measures 1 astronomical unit, about 150 million kilometers. Mercury, the closest planet to the Sun, sits at roughly 0.39 of that distance. Now, Spica AA and Spica AB lie separated by just 0.12 astronomical units. That's 4 times closer than Mercury is to the Sun, around 18 million kilometers. 2 objects, together weighing nearly 19 times the Sun's mass, squeezed into a space light crosses in about a minute. What happens to a body when another object of similar mass hovers nearby? It's like squeezing a ball of clay between your fingers. The ball stretches. Each star's gravity pulls harder on the side facing its partner than on the far side. This difference in pull, known as tidal force, distorts both bodies. They stop being perfect spheres. Instead, they become stretched ellipsoids, bulging toward each other like two eggs pointed end to end. The plasma on their facing surfaces grows hotter. It ripples, almost touching. Both of these distorted stars are Beta Cephei type variable stars. Their surfaces don't just stretch under gravity, they also pulse. They rhythmically contract and expand, almost as if the stars themselves are breathing. Their pulsation cycle lasts just a few hours. Their brightness changes, their shape shifts. Two flattened giants breathing 18 million kilometers apart, yet no telescope can resolve them separately. But here's the catch. In such a tight pair, that close together, tidal forces usually do one more thing. They synchronize rotation. Each star should show the same face to its partner, just like the moon does to Earth. Gravity slows them down, aligns them, locks them in place. It's only a matter of time. And that's the key word: time. The spins of Spica AA and Spica AB don't line up. Each one turns at its own pace, its own speed, like two gears that haven't yet locked teeth. The system is too young. It's about 12.5 million years old. By comparison, our sun is 4.5 billion years old. Spica is roughly 360 times younger than the sun. In cosmic terms, it's practically a newborn. Its internal mechanics haven't settled down yet. Gravity is still at work. That means the system keeps evolving. Tidal forces are still slowing their spins. The orbit is shrinking. These two distorted, pulsing giants are inching closer, slowly, but with every rotation a little tighter. From the outside, it looks like a smooth white-blue dot in the constellation Virgo. But inside, there's 18 million kilometers of chaos, still far from settling down. Spica reveals how gravity crushes stars into tight embraces, reshaping perfect spheres into pulsing ellipsoids. But what happens when that same force fails to keep a star close to its partner, and instead flings it into open space at speeds so high they melt the surrounding interstellar medium? 440 light-years away. Closer than the Scorpius-Centaurus association, closer than most of the bright stars in the night sky. And right now, at that exact distance from us, a clue is hurtling through space. A blue giant, 20 times more massive than the sun, alone. No companion, no cluster, no obvious reason to be where it is. Zeta Ophiuchi, a massive blue giant all by itself. That's already unusual. These stars form in tight star nurseries, dense molecular clouds teeming with dozens, sometimes hundreds of siblings. They don't wander the galaxy on their own. If you spot a blue giant outside a cluster, it means someone shoved it out. And here is where the real detective work begins. By analyzing the movement of Zeta Ophiuchi, its speed, direction, and trajectory, we learn something clear. This star used to belong to the Scorpius-Centaurus association, the very same group we've already encountered during our investigation. But then, some cosmic catastrophe happened. A supernova explosion of its companion in a tight binary system, or the gravitational slingshot effect from a close encounter with several massive stars, and Zeta was thrown out, cast away. Now, it's speeding away from its birthplace like a cannonball shot out of a barrel millions of years ago. This isn't a metaphor. It's an exact description. You might expect a star shining with 74,000 times the energy of our sun to be one of the brightest points in the sky. Its surface temperature exceeds 35,000 kelvins, 6 times hotter than our star. Yet, to the naked eye, Zeta Ophiuchi appears surprisingly modest. The culprit? Interstellar dust. These clouds of matter, scattered by explosions from earlier generations of stars, absorb a large portion of its light. It blazes like a spotlight behind fog. immensely powerful, but dim to our eyes. Yet, this dust reveals something else entirely. Zeta Ophiuchi isn't just flying through space. It slices through the interstellar medium like a bullet through water. A fierce stellar wind, blasting from its scorching surface, crashes into the gas and dust ahead. This collision creates a glowing shockwave, a fiery arc of heated material, a crescent of hot gas glowing in infrared light. It's like the wake behind a ship, but the ship is a star 20 times the mass of our sun, and the water is the thin, almost invisible interstellar gas. This shockwave makes the unseen visible. It reveals something racing forward, fast, for a long time. Now, let's change our perspective. Forget the arc, forget the path. Let's zoom in. What do we see? Not a sphere. Zeta Ophiuchi spins so fast that it completes a full rotation in about 1 Earth day. By comparison, our sun takes 25 days to turn once. At the equator, Zeta's speed reaches 400 kilometers per second. That's 1.5 million kilometers per hour. At that pace, you could travel from New York to Los Angeles in less than 4 seconds. The centrifugal force from this rapid spin literally stretches the star outward. Its equatorial radius is more than 9 times larger than the sun's, while the polar radius is only about 7.5 times bigger. That's a difference of nearly 20%. This star isn't just a sphere with a slight bulge. It's a swollen, flattened disk, like a plasma mandarin whose temperature drops from pole to equator, because the stretched surface at the equator sits farther from the core, making it cooler. This kind of distortion isn't nature acting on a whim. It's a mark left by the very event that blasted the star out of its home. A gravitational slingshot, or the explosion of a companion star, could have spun Zeta up to its breaking point. It carries the scar of that catastrophe, not as a crack, but in the shape of its very body. And here's what's hard to grasp. Zeta Ophiuchi is 3 million years old. 3 million. Our sun is 4.5 billion years old. Zeta is 1,500 times younger than the sun. By cosmic standards, it's a newborn, fresh out of the cradle. Yet it has already lived through half of its life. In a few million years, the nuclear fuel in its core will run dry. It will swell into a red giant, then explode as a supernova. A star that was born yesterday on the galactic clock will die tomorrow. The sun still has 5 billion years to go. Zeta won't even make it past 10 million. Mass is a sentence. The heavier a star, the faster it burns through its fuel, the brighter it shines, and the quicker it dies. 20 times the mass of our sun doesn't mean 20 times the life. It means a life cut short 1,000 times over. And when Zeta finally blows up, and it will, the shockwave from that explosion will ripple through the neighborhood. It will slam into those clouds of dust and gas hanging quietly in our corner of the galaxy. It will compress them, densify them, and maybe even spark a process that leads to the birth of new stars. Zeta Ophiuchi isn't just a runaway star. It's a living, speeding, spinning testament to how the space around us is sculpted by explosions. This star projectile carries on its flattened body the memory of forces powerful enough to hurl an object 20 times the mass of the sun across half the galaxy, without even breaking a sweat. Zeta isn't the only star nearby heading toward its final act. There's another, brighter, closer, and its end will be visible from Earth without any telescopes. Spica, the brightest star in Virgo, a bluish-white point shining in the spring sky. It's a binary system. 2 massive stars locked in a tight dance, orbiting each other so closely they're only 18 million kilometers apart. That's less than the distance from Mercury to the Sun. These 2 blazing balls of plasma distort each other with tidal forces, stretched out like eggs, their pointed ends facing one another. Here's what happens inside the primary star. Its core runs out of hydrogen, The nuclear fusion reactor, burning steadily for millions of years, reaches the point where it has no more fuel. According to models of stellar evolution, soon, by cosmic standards, the star will start to expand. Its outer layers will swell, pushing past the gravitational boundary between the two stars and flowing onto its companion. A stream of hot gas moving from one star to the other. Not an explosion, not a flare. A slow, relentless transfer of matter, like one container overflowing into another. This process is called accretion. Simply put, the star begins feeding its neighbor with its own flesh. At first glance, the star's mass would simply shift and settle down. But that very shift sets off an irreversible chain reaction. In a few million years, the accumulated mass and the collapse of the core will trigger a Type II supernova explosion. And Spica is the closest star to Earth likely to go supernova, 260 light-years away. In galactic terms, just next door. First, the core compresses. The iron at the star's center stops producing energy. This is the element where nuclear fusion first begins to fail. The core collapses inward in a fraction of a second. With its support gone, the outer layers fall in too, then bounce off the unimaginably dense core. They explode outward in every direction, racing at tens of thousands of kilometers per second. The explosion will be visible in broad daylight. For several weeks, a new bright spot will blaze in Earth's sky, brighter than any star, possibly even outshining the full moon. Then it will fade. The gas shells will spread out, cool down, and blend into the interstellar medium. What remains of the dazzling binary system will be a tiny neutron star, a sphere about 12 miles across, roughly the size of a city. Yet a single tablespoon of its material would weigh around 1 billion tons. That's all that will be left of Spica. 2 suns shrunk down to a single point. And here the second part of the story begins. Because the expelled matter doesn't just vanish. It drifts through space, enriching it with heavy elements. Carbon, oxygen, iron, all the building blocks for future planets. And it finds a place to settle. 600 light-years from Earth, in the constellation of the Southern Cross, hangs something best described as a hole in the sky, the Coal-Sack Dark Nebula. It's part of the same Scorpius-Centaurus association that includes Spica and Zeta Ophiuchi. Against the glowing band of the Milky Way, it appears as a void. A black spot with not a single star inside. Not because stars are missing there, but because a dense cloud of cold dust and gas blocks all the light from the stars behind it. Its diameter stretches between 30 and 35 light-years. But the strangest thing is its apparent size. In the night sky, the coal sack covers an area 138 times larger than the full moon. You could fit 138 moons into that darkness. Yet, standing under the southern sky, looking straight at it, you see nothing. Pure darkness against the starry milk of the galaxy, the most striking invisible object in the night sky. Inside this cloud, temperatures plunge to between 10 and 20 kelvins. That's about minus 253 degrees Fahrenheit, colder than the shadow of Pluto. Hydrogen molecules and specks of dust drift slowly in complete darkness, unaware of what lies ahead. And what awaits them is exactly what has already happened to other clouds like this. In a few million years, the galaxy's rotation will shift the coal sack closer to bright stars, causing it to glow with reflected light. But that's just the beginning. The cloud's own gravity, slow and patient, will start pulling matter toward its center. Density will increase, temperatures will rise. At a certain point, in the densest knots, pressure and heat will reach a threshold where hydrogen begins fusing into helium. New stars will ignite. Not just one or two, an entire cluster. The coal sack will transform into a scattered star cluster. Where there is now darkness and cold, tens of young stars will blaze in a few million years. Some of them might even form planets, from the very material once blasted out by explosions of stars like Spica. An explosion creates a cloud. The cloud births stars. Stars burn, age, and explode. New clouds form. New stars emerge. It's a cycle without a beginning or an end. just a constant remixing of the same material. With each turn, it grows a little more complex, a little heavier, a little more ready to one day come together into something that can ask questions about its own origins. While some nebulae are just gearing up to ignite their first generation of stars, entirely different stories unfold in clusters where stars have been burning bright for ages. These are not tales of birth or death, but stories of survival at the very edge of possibility. 215 kilometers per second. That's how fast the equator of Alcyone A, the main star of the brightest light in the Pleiades, spins. That's about 100 times faster than our sun rotates. To grasp what this means, imagine a playground carousel. You spin it, faster, even faster. At some point, a child won't be able to hold on. The centrifugal force just throws them off. The same thing happens with Alcyone, but instead of a child, it's scorching plasma flying off. And instead of a carousel, it's a star with 6 times the mass of our sun. Alcyone, the star in Taurus, lies about 440 light-years from Earth. It's not a single star, but a system made up of 4 components. Yet one star dominates, Alcyone A, a white-blue giant with a radius between 8.5 to 10 times that of the Sun. Its brightness outshines the Sun by more than 2,000 times. Simply put, if you replaced our Sun with Alcyone A, Earth would vaporize long before it could reflect any light. But the most dangerous thing about this star isn't its brightness. It's how fast it spins. At 215 kilometers per second along its equator, this star literally loses its shape. It's not round. Instead, it flattens out like a mandarin crushed between your palms. The centrifugal force at its equator almost matches gravity, so plasma particles break free from the surface and shoot outward. But they don't scatter randomly. They form a glowing ring, a hot, dusty disk made of material the star can no longer hold on to. Alcyone A isn't just spinning, it's tearing itself apart. And that raises a question that haunts astronomers. How did it end up in the Pleiades at all? The Pleiades star cluster is about 130 million years old. Alcyone A, its brightest star, is roughly 70 million years old. That means it's half the age of the cluster it calls home. Imagine finding a building in a historic neighborhood that was just built yesterday, and yet it sits right at the most prominent spot. One explanation? Alcyone didn't form here. It was captured by the cluster's gravity after the rest of the stars had already settled, a cosmic interloper pulled in by neighboring stars claiming a central position. The brightest star in the Pleiades might actually be an outsider, but the Pleiades aren't the only cluster full of surprises. About 150 light-years from us, in the Hyades cluster, an older group already breaking apart, we found something unexpected. Not a star, a planet. Epsilon Tauri, also known as Ain, shines as one of the brightest stars in the Hyades cluster. It's an orange giant, weighing 2.7 times the mass of our Sun, with a radius more than 12 times larger and shining 80 times brighter. A massive, mature, and steady star. But in the year 2007, astronomers found something around it that had never been seen before in any open star cluster. An exoplanet. They named it Amaterasu. It became the first exoplanet discovered inside an open cluster. This wasn't a fluke. Scientists had suspected for decades that planets should form in clusters. Yet the gravitational chaos from nearby stars seemed like it would tear any forming system apart. Amaterasu proved that assumption wrong. So, what kind of world is this? A scorching hot super-Jupiter. It has a mass 7.6 times that of Jupiter. Its radius is 18% larger than Jupiter's. The average surface temperature hits 541 Kelvin. That's 268 degrees Celsius. Hot enough to melt tin. This planet orbits around Ain in 645 days, tracing a stretched elliptical path. Its average distance from the star is 1.9 astronomical units, just a bit farther than Mars is from our Sun. Here's what really stands out. Amaterasu survived. The Hyades cluster is losing stars. The Milky Way's gravity is stretching it apart, scattering its stars in every direction. In a few 100 million years, the cluster will no longer exist as a single unit. Yet the planet, a gas giant more than 7 times the mass of Jupiter, blazing at 268 degrees, continues its 645-day orbit around the dying giant, as if nothing has changed. A star scattering its own matter. A giant that may have wandered into its cluster from afar. A planet that shouldn't have survived the gravitational chaos of an open cluster. Yet it did. Each of these objects shatters our expectations about what a normal star system should look like, and they all lie just a few hundred light years away, clustered in a tiny patch of space we're only beginning to explore in depth. Among all the objects we've examined in this investigation, one remains unanswered. The neutron star, catalogued as RxJ 1856.5-3754, the closest dead star to us, the very one we mentioned at the very beginning. Its anomaly once seemed like a mere statistical oddity, but now, after everything we've covered, it's time to return to it. Neutron stars appear in the universe about 1,000 times less often than ordinary stars. For every 1,000 regular stars, there's one dense core left behind after a supernova explosion. Finding one nearby is already a stroke of luck. But finding a hot one, that's a whole different story. At birth, a neutron star's temperature can soar to several million Kelvin. But they cool down fast. Really fast. Now this particular star, about 12 kilometers in radius, less than half the width of the beltway around Moscow, is glowing at 250,000 Kelvin. For an object like this, that's an unusually high temperature. It should have cooled off long ago. But it hasn't. Discovering a hot neutron star this close is like stumbling on a fresh ember in a campfire that was put out a full day ago. Embers don't stay that hot. And neither do stars. Something is holding on to that heat, and that's where things get really strange. In 2016, while observing light passing near this star, astronomers discovered something no one had ever seen in nature before. The light split. It didn't scatter or get absorbed. It split into 2 beams with different polarizations. In empty space. In a vacuum. Where, supposedly, nothing should affect photons. This phenomenon is called vacuum birefringence, or the Euler-Heisenberg effect. Simply put, empty space behaved like a crystal, like a piece of Iceland spar that doubles an image when you place it over text. But here, the crystal was the vacuum itself, twisted and warped by the monstrous magnetic field and gravity of a dead star. This effect was first predicted on paper. Then, scientists recreated it in laboratories under carefully controlled conditions, using some of the most powerful lasers in existence. But it wasn't until 2016 that they finally observed it where it originated, at the surface of the neutron star RxJ 1856.5-3754, located 400 light-years from Earth. Wait, let's pause and take this in. The cosmic vacuum, what we usually think of as absolute emptiness, the absence of everything, turns out to be a medium you can actually distort, one that can bend light. Not gas, not dust, not matter, space itself. Gravity and magnetism so intense they warp the optics in a place where you wouldn't expect anything to bend. And here, the investigation comes full circle. We started with a simple question. What's out there? Right next to us in space? The answer seemed obvious. Nothing. Just cold emptiness, sprinkled with distant pinpoints of light. But every step we took uncovered something different. Exploding supernovae carving out giant bubbles in interstellar gas. Stars shedding their own material into the void. Planets surviving in the chaos of gravitational maelstroms. And finally, the vacuum itself bending light like a lens. Empty space was anything but empty. That's the first revelation. Now, let's pull back. All this turmoil, the local bubble, nearby star clusters, blazing neutron stars, and warped vacuum spans a region stretching several hundred light-years across. That sounds huge, but this region is just a tiny patch on the very edge of the Orion arm of our galaxy, one of the spiral arms of the Milky Way, and not even the main one, more like a branch nestled between the Perseus and Sagittarius arms. We live on the outskirts of an outskirts. Even farther out, against the backdrop of the entire galaxy, 100,000 light-years across, with 400 billion stars, our little corner barely registers. It's a speck. Not even a speck, more like a tiny margin of error on a vast map. And the galaxy itself? It belongs to the local group. The local group is part of the Laniakea supercluster. Laniakea threads through a cosmic web of clusters and voids, stretching across billions of light-years. Everything we've examined so far, every explosion, every anomaly, every fractured beam of light, fits into a speck of dust invisible at this scale. Here lies the paradox we've been building toward. The void around us, it's not empty. It churns, it erupts, it warps the very laws of optics. Its complexity demanded decades of study and the use of orbiting telescopes. And yet, it's nothing. A microscopic detail, statistical noise on the edge of one arm of a single galaxy among trillions. We live inside the most intricate nothing in the entire universe. The stubborn Werner Heisenberg, who recorded an effect once considered pure abstraction for half a century, would probably appreciate the irony. Meanwhile, the neutron star RxJ1856.5-3754 keeps shining. 12 kilometers of compressed matter, a scorching 250,000 kelvins, a vacuum ripped apart around it. And all this lies just 400 light-years from a planet where someone right now gazes into the night sky and sees nothing but darkness.